Okay, so I want to kind of review the watermelon problem we just did. So we had a watermelon, 2 kilograms, dropping at 4 meters. And the question in the end, a couple questions. How fast is it going when it lands? And then how much cushion would we need to slow it down if it's going to break with 1400 newtons on it? Okay, so how did we do that? Well, we used some kinematics equations. Kinematics, fancy word for linear motion. Um, to do, grab my pen here. Originally, we could use this equation, the how far equation, and the how fast equation. In combination, we could have solved for the time and then plug that in to find final velocity. Or we use a bit of algebra to combine these two equations and we get this equation, which is super useful in cases like this, where we don't have the time and we just want to get from distance right to velocity. So, all right, we can use this one. We plug in what we know. The initial drop is 0 meters per second, or 0 meters per second. Acceleration due to gravity, let's assume it's about -10 because it's negative downwards. -4 meter drop because it's dropping downwards. That displacement is negative. So we get a square root of 80, and we get a final velocity of about 8.9 meters per second. Oops, just not per second. No one corrected me on that. Don't let me get away with that kind of stuff. Okay, so that's how fast it's going right before it hits the ground. So then we want to look at the collision. So if that's true, if it can only survive 1400 newtons, which to be fair is just what I asked Alexa what a watermelon would survive, and she actually answered, so I don't know how she knows that. Didn't verify it myself, but I'm going with it. So we have a force applied of 1400 newtons times the time that we don't know. We don't know how long it would take if we only want to apply 1400 newtons. Mass of 2 kilograms and a change in velocity of, it's going to end, its ending velocity, final velocity is 0. And the initial velocity here, because the final velocity of the drop is the initial velocity for the crash, that's what it's coming in with, is negative 8.9, that's downwards, right? So this should have been a negative 8.9. No one else pointed that out either. Don't let me get away with this stuff, because it's downwards. So we have a change in velocity of 8.9 meters per second. 2 times that is 17.8 kilogram meters per second. So that's our change in momentum. If we divide by the 1400 newtons, we get about 0.0127 seconds. So it's pretty quick, just over 100th of a second, and that watermelon goes smush. So, okay, if this takes any longer than that, if we can increase the time, we save our watermelon, which is what we want to do. We want to make sure the time is at least that much or higher, because if it's higher, then my force will be lower than that, and we have saved the watermelon. So, how do we do that? Well, we started asking the question, well, how much does it have to decelerate there? What's the deceleration in that moment? Well, our change in velocity over time is our acceleration, right? So if you go, the final velocity is 0 minus the initial velocity, so again, a change of 8.9, divide by 0.0127, our time. And by the way, if you have the original number in your calculator to a couple extra digits, it always helps to not round in the middle, but be that as it may. If we divide that out, we get an acceleration of 700.79 meters per second, which is pretty high. That if we want to figure out how many G's that is, we divide by 10. That's like that watermelon would be pulling 70 G's, which is a lot, right? Which is why it would probably break at that point. So we want to decrease that, increase the time. But why did we find the acceleration? And it's because we could go over here to our displacement equation, the how far equation. So when we asked if it's going to decelerate by the 700 meters per second, how thick does that actual cushioning, the padding, need to be to save the watermelon? Well, in that displacement, the thickness of it, it has to go from that velocity to 0. So it really has to decelerate. This becomes a linear motion problem again. So we plugged in our acceleration, we plugged in our time, we plugged in the initial velocity of negative 8.9, right? We crunch some numbers and we get 0.05657 meters, or about 2.2 inches. That's the padding we need to save our watermelon.